You stepped on a scale this morning, or last week, and a number looked back at you, and you accepted it without a second thought, the way you accept the color of your own eyes. It is simply how much of you there is. More of you, a bigger number. That feels far too obvious to ever question. But that number is almost entirely a lie about what you are actually made of. Follow your own weight downward, past the cells, past the atoms, down to the smallest pieces of you, and the idea that mass is just a measure of stuff falls apart at every single step. The particle that gives your atoms their shape, the electron, has no size at all, no inside, nowhere to keep the weight it so plainly has. And when you finally find where the weight really lives, it is not in any material. It is hiding in an invisible field that fills all of empty space, and in the trapped fury of a force locked inside particles too small to picture. Almost nothing you weigh is stuff. So where does it come from? Get comfortable. Hit subscribe if you're new here, because by the end of this, the number on your scale will never feel like a simple fact again. Now, let's slowly ease into this. Part 1. The weight you never question. There is a number you carry with you everywhere, and you almost never think about it. It is your weight. You stepped onto a scale this morning, or last week, or at some doctor's office years ago, and a figure looked back at you, and you accepted it the way you accept the color of your own eyes. It is simply a fact about you. It feels as ordinary as anything could possibly feel. And yet, if you stop and ask where that number actually comes from, you will find that almost nobody can tell you, and that the real answer is one of the strangest stories physics has ever uncovered. So, let us ask it slowly, the way you might turn an unfamiliar object over in your hands. Where does your weight come from? The easy reply is that you are made of a certain amount of material, and weight is just the measure of how much material there is. More material, more weight. That feels obviously true, but it only pushes the question back a step, because now we have to ask what that material is and where its weight comes from. And we can keep asking that question all the way down, smaller and smaller, until we arrive at the smallest pieces of you that exist. And when we get there, something very quietly goes wrong with the easy answer. Tonight we are going to follow that question down to its very bottom, and we are going to do it through a single particle, one of the simplest and most familiar objects in all of nature, the electron. It sits in every atom of your body, in the screen or speaker you are listening through, in the wire carrying the electricity that powers it. It is one of the most thoroughly studied things in the history of science. And if you ask the simple question, where does an electron get its mass from, you will find that the honest answer was not even guessed at until the 1960s, was not confirmed until the year 2012, and still, even now, contains a hole that nobody on Earth knows how to fill. I want to be clear about what kind of journey this is. This is not a story about something far away, some distant star, or some violent corner of the cosmos. This is a story about you, about the actual substance of your hands and the actual reading on your bathroom scale. By the time we are finished, you are going to understand that the weight you have carried your whole life is not made of what you think it is made of. It is built out of something you cannot see, something that fills the empty space around you right now, and something even stranger hiding inside every particle you are built from. Let us begin with the electron itself, because to ask where it gets its mass, we first have to appreciate how little there is to it. An electron has a definite mass. Physicists have measured it to an absurd precision. In everyday units, it comes out to about 9.1 times 10 to the minus 31 kilograms, which is such a small number that writing it out longhand would mean a decimal point followed by 30 zeros before you reach the 9. Particle physicists prefer a different unit, and in their language, the electron weighs about 0.511 mega-electron volts. You do not need to hold on to those numbers. The only thing that matters is this. The electron is real. It is everywhere inside you, and it has a specific, reliable, measurable weight. And here is the first quiet shock. The electron, as far as every experiment ever performed can tell, has no size at all. It is not a tiny ball. It is not a little speck of material. It is what physicists call a point particle, a thing with no width, no interior, no surface, no parts. We have looked very hard. We have smashed electrons together at nearly the speed of light, and we have measured how they scatter, and every measurement says the same thing. If the electron has any size, it is smaller than 10 to the minus 18 meters, which is more than 1,000 times smaller than the proton it orbits, and the results are perfectly consistent with the size being exactly 0. So sit with that for a moment, because it is the seed of the entire mystery. You have a thing with no size. It takes up no space. There is no inside to it where stuff could be stored, and yet it weighs something. It resists when you push it. It has the property we call mass. Our easy answer was that weight is the measure of how much material is packed into a thing. But the electron has no room to pack material into. It is a location with a few properties attached and nothing else. Where, in a thing with no volume, could its weight possibly be kept? This is the trapdoor under the ordinary idea of mass, and once you see it, you cannot unsee it. We tend to imagine that heavy things are heavy because they are full, crammed with substance, and that light things are light because they are mostly empty. That picture works well enough for boxes and bricks. It falls apart completely at the level of the electron, because the electron is as close to nothing as an object can be, while still being a real object, and it still tips the scale. Whatever mass is, it is not simply a count of how much stuff is present. It cannot be, because here is a thing with no stuff at all, and it has mass anyway. You might be tempted to say, well, the electron is a strange exception, a quirk of the very small that has nothing to do with my actual body. But that instinct is exactly backwards, and showing you why is most of what tonight is about. The electron is not an exception. It is the clearest possible window into how mass really works, precisely because it is so simple. There is nothing inside it to distract us, no internal machinery to hide behind. When we ask where its mass comes from, there is no easy place for the answer to hide. The electron forces the universe to show its hand, and the hand the universe shows is genuinely difficult to believe the first time you hear it. The mass of the electron is not something the electron owns. It is not stored inside the particle, because there is no inside. It is not a quantity of material, because there is no material. The mass of the electron is generated, moment by moment, by the electron's relationship to something else, something that is everywhere around it, something you are sitting inside of at this very second, without feeling a thing. The electron, on its own, stripped of that relationship, would have no mass whatsoever. It would fly through the universe at the speed of light, weightless, unable ever to slow down, unable ever to be still. That is where we are heading. But to understand why physicists were driven to such a wild-sounding conclusion, we have to first watch the comfortable, common-sense picture of mass collapse completely. We have to follow the material of your body down past the cells, past the molecules, past the atoms, all the way to the smallest pieces, and watch the idea that mass means stuff dissolve at every step. Because only when the old answer is truly gone will the strange new one feel less like a fantasy and more like the only thing left standing. So let us start that descent, and let us begin with the most familiar building block of all, the one you learnt about as a child, the atom and the surprising emptiness waiting inside it. Part 2, the answer that falls apart. We are going to take the easy answer about mass and follow it downward until it breaks, and the best place to start is with your own hand. Hold it up, or just picture it. It has weight. Set it on a table, and you can feel the table pushing back to hold it. That weight feels like a solid, simple thing, the sum of all the material your hand is made of. So let us start cutting that material into smaller and smaller pieces, and watch where the weight actually lives. Your hand is made of cells, billions of them, and each cell is made of molecules, enormous numbers of them, proteins and water and fats arranged into living machinery. So far, the easy answer holds up fine. The weight of your hand is the weight of all its cells, and the weight of each cell is the weight of all its molecules. Nothing strange yet. We are just adding up smaller and smaller bricks. Keep going. Each molecule is made of atoms, bonded together. A water molecule is 2 hydrogen atoms and 1 oxygen atom. The weight of the molecule is the weight of those 3 atoms together. Still fine. Still just counting bricks. Now we reach the atom, and this is where the first real surprise is waiting, because the atom is almost entirely empty. If you have heard this fact before, I want you to hear it again as if for the first time, because people repeat it so casually that its strangeness has worn off, and the strangeness is the whole point. An atom is a tiny, dense nucleus at the center, with a cloud of electrons around it, and between them is nothing, not air, not some thin material, nothing at all, empty space. Let me give you the scale of that emptiness, because the numbers are hard to believe. If you took the nucleus of an atom and made it the size of a marble and set it down in the middle of a sports stadium, the electrons would be tiny specks, flickering somewhere up in the very back rows, and everything in between, the entire volume of the stadium, would be empty. That is not a loose comparison. That is roughly the actual ratio. The atom is something like 99.999% empty space by volume. The solid floor you are sitting above, the firm table under your hand, the apparently continuous material of your own body, is almost entirely a vacuum with a few specks scattered through it impossibly far apart. So already the easy answer is in trouble. If matter is mostly empty space, then weight cannot be coming from the volume of stuff, because there is almost no stuff there to speak of. The weight must be concentrated in those few tiny specks, the nucleus and the electrons. Fine, we say, a little rattled, but still standing. The weight lives in the specks. Let us go look at the specks. And when we do, the easy answer takes its next blow, because the 2 kinds of specks are wildly unequal. Almost all of an atom's weight, it turns out, is in the nucleus. The electrons contribute almost nothing. A single proton in the nucleus weighs about 1,836 times as much as a single electron. Picture that ratio for a moment. If an electron weighed as much as a single apple, a proton would weigh about as much as 2 large adult men. The electrons whirling around the outside of the atom, the ones that do all the chemistry, that form every bond, that make fire and life and electricity possible, together make up only about 3 or 0.04% of the atom's total weight. They are almost weightless passengers riding around a heavy core. This is genuinely worth pausing on, because it overturns a picture most of us carry without realizing it. We tend to imagine the electrons as a significant part of the atom, since they are the busy, active part, the part that touches the world. But on the scale, they barely register. Your weight is almost entirely the weight of the nuclei buried at the centers of your atoms. The electrons that make you chemically you, that hold your molecules together, are a rounding error on the bathroom scale. Keep that fact in your pocket. It is going to come back later in a way that completely reshapes this story. So now we follow the weight into the nucleus, where almost all of it lives. The nucleus is made of protons and neutrons, packed tightly together. Surely here, at last, in this dense little knot at the center of the atom, we will find solid stuff, real material, the true source of the weight. And so we cut the proton open, metaphorically, to see what it is made of. And inside the proton, we find 3 smaller particles called quarks, 2 of one kind and 1 of another, held together by the strongest force in nature. Good, we think. The proton is made of quarks. The weight of the proton must be the weight of its 3 quarks added up. We have finally reached the bottom, the real bricks, the genuine stuff. Except that when physicists weigh the 3 quarks inside a proton, and then weigh the proton itself, the numbers do not match. They do not even come close. The 3 quarks inside a proton, added together, account for only about 1% of the proton's total weight. 1%. The other 99% is unaccounted for by the material inside. You take the bricks, you add up the bricks, and the bricks come to almost nothing compared to the wall they supposedly build. The proton weighs about 100 times more than the things it is made of. Stop and feel how strange that is, because it is the moment the easy answer dies completely. We started by saying, weight is just the amount of material. We followed the material down through cells and molecules and atoms, watched it nearly vanish into empty space, found the weight concentrated in tiny nuclei, cut those open, and arrived at the quarks, the supposed final bricks. And the bricks do not weigh enough. Almost all of the proton's mass, and therefore almost all of your mass, is not the weight of any material at all. It is coming from somewhere else, from something that is not stuff. It is worth pausing to remember that nobody expected the atom to be this empty, and that the discovery was an accident that shocked the man who made it. A little over 100 years ago, a physicist named Ernest Rutherford had his students fire tiny positively charged particles at an extremely thin sheet of gold foil, expecting them to pass almost straight through. Since the prevailing idea was that an atom was a soft, evenly spread blob of charge. Most of them did pass straight through, but every so often one came bouncing almost directly back, as if it had struck something incredibly hard and small. Rutherford famously said it was as astonishing as if you had fired a heavy shell at a sheet of tissue paper and watched it ricochet back and hit you. The only way to explain it was that nearly all the atom's mass and all its positive charge were crammed into a minuscule core at the center, with the rest of the atom being empty space. The emptiness was not a theory anyone wanted. It was forced on physics by a particle bouncing the wrong way. That emptiness has a consequence worth dwelling on for a moment, because it makes the solidity of the world even stranger. When you press your hand against a table, nothing actually touches in the way you imagine. The atoms of your hand never make contact with the atoms of the table, because atoms are mostly void and the specks within them never meet. What you feel as solid contact is the electric repulsion between the outer electrons of your hand and the outer electrons of the table. 2 clouds of charge pushing against each other across a gap that, on the atomic scale, is enormous. Solidity is not stuff meeting stuff. It is fields pushing on fields across mostly empty space. And if even the touch of a table is an illusion of fields rather than a meeting of substance, then the weight of that table is about to turn out to be just as strange. We will come back to where that 99% comes from, because it is one of the 2 great revelations of this whole story, and it deserves its own chapter to land properly. But notice what has happened to our simple question. We asked where the electron gets its mass, and the electron turned out to have no size to keep mass in. We asked where your body gets its mass, and your body turned out to be mostly empty space wrapped around tiny cores whose own weight is mostly unaccounted for. At every level, the idea that mass is just a pile of material has fallen apart in our hands. Whatever mass really is, it is hiding, and it is not hiding inside the particles. So before we can say where the electron's mass comes from, we have to confront the electron at its purest, the point with no size, and ask the question that has no easy escape. If there is nothing inside it, where is the weight? Part 3. The point with no size. I want to take you somewhere now. in your imagination, because the next idea is one you have to feel rather than just hear. We are going to shrink down, you and I, and go inside a single atom of your own hand, and we are going to look for the electron, and we are going to discover what it actually is, or rather, what it strangely is not. Begin at the scale you live at, the scale of skin and bone, and start falling inward. The surface of your hand rushes up and opens like a landscape made of cells, vast, soft structures drifting past as we descend. We fall through a cell wall into a crowded interior, then in further, past the tangled machinery of molecules, until we reach a single atom and slip inside its outer boundary. And here, suddenly, everything goes quiet and empty. We are inside the atom now, and there is almost nothing here. Far below us, impossibly far on this scale, a tiny dense knot waits at the center. That is the nucleus. And somewhere around us, somewhere in this enormous emptiness, is an electron. We came to find it, so we look. But finding the electron is not like spotting a small ball floating in the dark. As we move toward where it should be, there is no surface that rises to meet us. There is no skin, no boundary, no little sphere growing larger as we approach. We reach the place where all our instruments say the electron is, and there is simply a point, a location. A place where the electron's properties are concentrated, where its charge is, where its mass makes itself felt, and yet there is nothing there to touch. No matter how far we shrink down, no matter how close we bring our eyes, the electron never resolves into an object with parts. It stays a point, infinitely small, a thing that takes up no space whatsoever, while still, somehow, being absolutely real. This is not a limitation of our imaginary submarine. This is the actual finding of a century of experiments. The electron has no measurable size, and everything we know is consistent with it being a true geometric point. And standing there in the emptiness, looking at this sizeless thing that nonetheless has weight, you finally feel the full force of the problem in your gut. Weight, mass, the property that makes the scale move, is sitting in front of you in a thing with no inside. There is no container. There is nowhere for the weight to be kept. And yet it is undeniably there. Let me make the strangeness sharper, because it deserves to be uncomfortable. Throughout history, every time we found that something had weight, we could always point to what carried it. A stone is heavy because of the rock it is made of. The rock is heavy because of its minerals. The minerals are heavy because of their atoms. Always, the weight had a home, some material you could point to. The electron is the first place that chain truly ends, and when it ends, there is nothing there. It is as if you followed a sound back to its source, and found that the source was an empty room. The weight is real. The thing carrying it has no substance to carry it with. So what do we do with that? For a long time, physicists tried to escape the problem in a clever way. Maybe, they thought, the electron only looks like it has no size because we have not looked closely enough. Maybe it really is a tiny ball, just smaller than we can currently measure, and its mass is the mass of that tiny ball of material. It was a reasonable hope, but it led straight into a disaster, and the disaster is worth understanding because it is one of the most beautiful dead ends in the history of physics. Around the beginning of the 20th century, before anyone knew about quarks or fields in the modern sense, some of the greatest physicists alive tried to calculate the electron's mass by assuming it came from the electron's own electric charge. An electron is electrically charged, and a charge carries energy in the electric field around it, and energy, as we will see, is related to mass. So they reasoned that the mass of the electron might be nothing more than the energy stored in its own electric field. It was an elegant idea. Mass as self-energy. The electron would be heavy because of the effort of holding its own charge together. For a while, it looked like it might even work. But then they tried to make the electron a true point, with no size, and the mathematics exploded. The energy in the electric field of a charged point turns out to be infinite. The closer you squeeze the charge toward a single point, the more energy its field contains, rising without limit, until at zero size the answer is infinity. An electron built this way would have infinite mass, which is absurd, since the real electron is almost weightless. The elegant idea had collided with the electron's sizelessness and shattered. You could not build the electron's small, finite mass out of the energy of a point charge, because a point charge implied infinite energy. The dream of mass as self-energy died right there, on the rocks of the electron having no size. I tell you about that failure because it teaches the right lesson. The electron's lack of size is not a small technicality. It is a wall that destroyed the most natural theory of where its mass could come from. Any answer to our question has to survive the fact that the electron is a point. It cannot store its mass in material because there is none. It cannot store its mass in the energy of its own crushed-down field because that gives infinity. The weight is real, the particle is sizeless, and both of the obvious hiding places for the mass have been ruled out. Something genuinely new is required. And the something new begins with a shift so fundamental that we have to rebuild our idea of what mass even is before the real answer can make sense. Because here is the thread we have been circling. We keep asking where the mass is kept, as if mass were a substance that has to be stored somewhere. But what if that question is wrong? What if mass is not a thing that gets stored at all, but something more like a behavior, a relationship, an effect that arises when certain things interact? We already saw a hint of it with the proton, whose weight was 100 times more than its parts. That extra weight was not material. It was something else wearing the disguise of mass. To understand the electron, we now have to understand that disguise, and it begins with the most famous equation in the world, an equation almost everyone can recite, and almost no one has truly been allowed to feel. So let us go to that equation next, and discover that mass, at its root, was never made of stuff at all. Part 4. Mass was never made of stuff. Almost everyone can recite the equation, even people who never liked physics. Energy equals mass times the speed of light squared. You have seen it on posters and t-shirts. You probably learned that it has something to do with atomic bombs, with the idea that a little bit of matter can be turned into a great deal of energy. That is true, but it is also the smallest and least interesting thing the equation is telling you. The real message, the one that matters for tonight, is hidden in plain sight, and once you see it, you cannot weigh anything the same way again. The equation says that mass and energy are not two different things. They are the same thing, measured in different units, like distance measured in miles or kilometers. Anything that has energy has mass, and anything that has mass has energy, and the speed of light squared is just the exchange rate between the two. We are used to thinking of mass as solid and energy as ghostly, mass as the stuff and energy as what the stuff does. But the equation flatly denies that. It says they are one substance wearing two faces. Energy is not something matter contains. Energy is what matter is. Let me make this concrete, because it sounds like wordplay until you see it in action. Take a hot cup of coffee and a cold cup of coffee, identical in every other way. The hot one weighs very slightly more. It is heavier by an almost unimaginably tiny amount, purely because it contains more heat energy, and energy has mass. Wind up a spring, and it gains a feather's whisper of weight from the energy you stored in it. Squeeze any kind of energy into an object, and the object gets heavier, not because you added material, but because energy itself is heavy. The amount is far too small to ever notice in a coffee cup, because the speed of light squared is such an enormous exchange rate that a little mass equals a colossal amount of energy. But the principle is exact, and it is real, and it has been confirmed countless times. Now turn that around and point it back at our problem. If energy has mass, then a thing can be heavy not because it is full of material, but because it is full of energy. The weight does not have to come from substance. It can come from motion, from fields, from the sheer activity bound up inside a thing. And suddenly the impossible facts from earlier start to breathe. The proton that weighed 100 times more than its quarks, the weight that had no material to account for it. We were looking for missing stuff. There was never any missing stuff. There was missing energy, and energy weighs. This is the conceptual hinge of the entire night. So let me say it as plainly as I can. Mass is not a measure of how much material is in an object. Mass is a measure of how much energy is bound up in an object when it is sitting still. That is the honest definition, the one physicists actually use, and it is profoundly different from the schoolyard idea of mass as the amount of stuff. A thing is heavy when it contains a lot of energy in a confined, resting form. A thing is light when it contains little. The material, the stuff, was always beside the point. It was energy all along, and energy can live in places where stuff cannot, including inside a particle with no size at all. Do you feel the door opening? The electron has no inside, no room for material. But energy does not need a room. Energy is not a substance you stack up in a container. It is a property of relationships, of interactions, of fields stretching through space. An electron with no size can still sit in the middle of an interaction that carries energy, and that energy, by the most tested equation in physics, would show up as mass. The weight of the sizeless point does not have to be kept anywhere inside the point. It can come from what the point is doing, from how it is connected to the rest of the universe. So our question quietly transforms. We started by asking where the electron keeps its mass, imagining mass as a thing to be stored. Now we know that was the wrong question. Mass is bound energy. The real question is, what is the electron interacting with, so constantly and so universally that the interaction carries energy, and that energy shows up as the electron's weight? What is the source of the energy that the electron is forever steeped in, even when it is doing nothing, even when it is sitting perfectly still in the dark? And notice the demand hidden in that question, because it is very strict. Whatever the electron is interacting with has to be everywhere. The electron has mass, no matter where you put it, here on Earth, in the emptiest gulf between galaxies, inside a star, in a sealed laboratory, drained of all air and light. There is nowhere you can take an electron to make its mass go away. So whatever it is interacting with cannot be some special material that exists only in certain places. It has to fill all of space, uniformly, permanently. It has to be present in what we would normally call perfect emptiness. The source of the electron's mass has to be hiding inside the vacuum itself. That is a staggering requirement, and for a long time it seemed impossible. The vacuum, by definition, is what is left when you take everything away. It is supposed to be nothing. How can nothing be the source of an electron's weight? How can empty space reach into a particle and give it mass? For decades, this looked like a contradiction with no resolution, and physicists building their theories kept running into it from a different and even more painful direction, which we will come to in a moment. But the resolution, when it finally arrived, was to challenge the deepest assumption of all, the assumption that empty space is empty. Because here is what physics slowly, reluctantly discovered over the 20th century. The vacuum is not nothing. It is not an inert stage on which particles act. It is a churning, structured, physically active thing, filled with fields that are present everywhere, even when no particles are around. Space itself has properties. It can hold energy. It can carry influence. And one of those fields, it turns out, has a feature unlike any other. A feature that makes it the perfect candidate to be the source of the electron's mass. While almost every field in nature sits quietly at zero when left alone, this one does not. Even in the deepest emptiness, drained of all particles and all light, this one field holds a value that is not zero. It is switched on, everywhere, all the time, and it has been since the universe was a fraction of a second old. That field is what we now call the Higgs field, and it is the answer to our question, or at least the first and most important layer of the answer. The electron gets its mass by interacting with the Higgs field, a field that fills every cubic inch of the vacuum with a value that never turns off. The electron, dragging through that ever-present field, gains energy from the interaction, and that energy, by the equation we just rebuilt, is its mass. Take the field away, and the electron's mass would vanish, and it would streak off at the speed of light, weightless forever. The weight of the sizeless point comes not from inside it, but from the ocean it is swimming in, an ocean that is present even in what we call empty space. There is a way to see this principle at work that you may already half know about, because it powers the stars and it powered the most fearsome weapons ever built. Inside the sun, hydrogen nuclei are fused together into helium, and when they fuse, the helium that results weighs very slightly less than the ingredients that went into it. A tiny sliver of mass has gone missing. It was not destroyed. It was converted into energy, an enormous amount of it, by that same exchange rate, the speed of light squared, and that energy is the sunlight that crosses 93 million miles of space to warm your face. The sun is, quite literally, slowly converting its own mass into light, losing about 4 million tons of weight every second as it shines. The same arithmetic, run in reverse, is why a heavy nucleus weighs less than its separate parts would, and why pulling it apart or slamming light ones together releases the bound energy as a flash. Mass turning into energy, and energy turning into mass, is not an exotic possibility. It is happening above your head every daylit moment. So when we say that energy weighs, we are not making a clever philosophical point. We are describing the everyday engine of the cosmos. Every star shines by trading mass for energy. Every nucleus in your body is a little lighter than its parts, because some of its mass is bound up in the energy that holds it together, energy that registers, with a minus sign, on the scale. The world is full of mass becoming energy, and energy becoming mass, flowing back and forth across that exchange rate as easily as water changes between ice and steam. Once you accept that the two are one substance, the proton's missing weight stops being a paradox and becomes the most natural thing imaginable. The weight was energy. It was only ever energy. We had simply been taught to call it stuff. But I have been describing this field as if it obviously exists, as if physicists simply looked into the vacuum one day and saw it shining there. That is not how it happened, and the true story is far better because the Higgs field was not discovered by looking. It was demanded by a crisis, conjured on paper to save the equations of physics from collapse, years before anyone had the faintest evidence it was real. To understand why we believe in an invisible field filling all of space, we have to go back to the early 1960s into a problem so severe that it threatened to bring down the whole understanding of the forces of nature, and to the small group of physicists who, almost reluctantly, proposed the wildest fix imaginable. So let us go and stand in that empty vacuum one more time, and then watch where the idea of the field actually came from. Part 5. The field hiding in empty space. Before we go back to the crisis that gave birth to the idea, I want you to stand inside the vacuum for a moment and feel how full it is, because everything that follows depends on overturning your sense that empty space is empty. So come with me into a sealed chamber, a perfect one, better than any real laboratory could build. We pump out all the air, every last molecule. We cool the walls until almost no heat radiation remains. We block out all light. We remove every particle of matter we possibly can. By every ordinary standard, the chamber now contains nothing. It is as empty as a place can be, and yet it is not empty at all. Standing here, if you could perceive the fields that physics has revealed, you would feel that the chamber is filled, end to end, with a presence. The Higgs field is here, at full strength, exactly as strong in this sealed emptiness as it is in the center of a star or the space between galaxies. It does not glow. It does not push on you in any way you can sense. It carries no particles, no light, no heat. But it has a value everywhere, a number that physics assigns to every point in space, and that number is not zero. It is the same non-zero value through the entire universe, a steady, silent tone underlying all of reality. Physicists even have a figure for the strength of that ever-present value. In their units, it comes out to about 246. In the energy units they use for such things. You do not need the number, you need the feeling of it. Everywhere there is space, the Higgs field is switched on, holding that value, and it has done so continuously since the universe was less than a billionth of a second old. We are not surrounded by the Higgs field the way we are surrounded by air, which thins out and disappears as you climb. We are submerged in it the way a fish is submerged in the sea, except that this sea is in every location there is, with no shore and no surface, no place where it stops. Now, why does this one field behave so strangely? Almost every other field in nature, left undisturbed, settles down to zero. The electric field around an isolated neutral region is zero. Remove the magnets and the magnetic field goes to zero. Fields, as a rule, want to relax to nothing when nothing is stirring them. The Higgs field is the great exception. Its lowest energy state, its most relaxed and settled condition, is not at zero. It is at that non-zero value. For this particular field, switched on is more comfortable than switched off. Resting, doing nothing, undisturbed, it still holds its value, because for the Higgs field, holding that value is what resting means. Empty space, fully relaxed, is already full of it, and this is the property that makes it the perfect source of mass. Remember the strict requirement from before. Whatever gives the electron its mass has to be everywhere, permanently, present even in perfect emptiness. The Higgs field satisfies that requirement exactly, because it is the one thing that does not vanish when everything else is taken away. It is the flaw beneath the vacuum. So when an electron exists, anywhere at all, it is necessarily immersed in the Higgs field, because there is no anywhere that lacks it. The electron is never alone. It is always in contact with this universal presence, always interacting, and that ceaseless interaction is the origin of its weight. Now let me give you the metaphor everyone reaches for, and then let me immediately tell you how it lies to you, because the metaphor is useful and dangerous in equal measure. People say the Higgs field is like a thick fluid, like molasses or syrup, and that a particle moving through it is slowed and dragged the way you would be slowed wading through deep water. A heavy particle is one that interacts strongly with the syrup and gets dragged hard. A light particle barely interacts and slips through easily. A massless particle, like the photon, does not feel the syrup at all and sails through at full speed, the speed of light. As a first picture, that is not bad. It captures the central idea that mass comes from interaction with an all-pervading field, and that different particles interact by different amounts. But here is where the syrup metaphor betrays you, and you should hold on to this because it protects you from a real misunderstanding. Syrup slows things down. If the Higgs field were really like syrup, a moving electron would gradually slow to a stop, dragged to rest by the resistance, the way a marble sinks slowly through honey and halts. That is not what happens. An electron coasting through space does not slow down. The Higgs field does not act like friction. It does not steal motion. What it actually gives the electron is not drag, but inertia, which is a subtler and stranger thing. Inertia is not resistance to moving. It is resistance to changing how you move. It is the reason a heavy object is hard to get going and hard to stop once it is going, the reason it resists any push that would speed it up, slow it down, or turn it. The Higgs field does not slow the electron. It makes the electron stubborn, reluctant to change its motion, and that stubbornness, that reluctance, is exactly what we mean by mass. So replace the picture of wading through syrup with something truer, if harder to hold. The electron is not being dragged through the Higgs field. It is engaged in a constant back and forth with it, an interaction that happens at every instant, and the cumulative effect of that endless interaction is to give the electron a resting energy, a weight, an unwillingness to be pushed around. The more strongly a particle talks to the Higgs field, the more inertia it gains, and the heavier it is. The electron talks to it rather weakly, which is why the electron is so light. Some particles talk to it enormously more and are enormously heavier, and some, like the photon, do not talk to it at all, and so have no mass, and are condemned to fly forever at light speed, never able to rest. This single mechanism, this idea of an ever-present field that hands out inertia in proportion to how strongly each particle interacts with it, explains the masses of all the fundamental particles, the electron among them. It is not a vague philosophical notion. It is a precise piece of machinery, written in exact mathematics, that takes the strength of each particle's interaction with the field and returns that particle's mass. Feed in how strongly the electron couples to the Higgs field, and out comes 0.511 mega-electron volts, the measured mass of the electron, correct to as many decimal places as you care to check. The field is real, the mechanism is exact, and the electron's weight is its wage for never being able to stop interacting with the ocean it lives in. It helps, here, to be honest about what a field actually is, because the word gets used so loosely that it can start to sound like a fog or a vapor, and it is neither. In modern physics, a field is simply a quantity that has a value at every point in space and that can carry energy and influence. The temperature in a room is a humble field, a number at every location, warmer here, cooler there. The magnetic field around a magnet is a field that can push a compass needle from a distance. Physics has discovered that the deepest layer of reality is made entirely of fields like these, spread through all of space, and that what we call particles are really just localized ripples or excitations in those fields. The electron is a ripple in the electron field. Light is a ripple in the electromagnetic field. The world is not, at bottom, a collection of tiny balls. It is a set of fields filling space, and the particles are the trembling of those fields. Once you see particles that way, the Higgs field stops sounding like magic and starts sounding like one more member of a family you already accept. There is an electron field everywhere, an electromagnetic field everywhere, fields for every kind of particle, all of them filling space, whether or not any particles are present. The Higgs is just another such field, with one special trait the others lack, that it does not rest at zero. And here is the cleanest way to see what it does. The photon, the particle of light, is a ripple in the electromagnetic field, and it has no mass, because it does not interact with the Higgs field at all. So it can only ever travel at one speed, the speed of light, never faster, never slower, never still. The electron is almost the same kind of thing, a ripple in its own field, except that it does talk to the Higgs field, and that conversation is the entire difference between a particle that must fly forever and a particle that can come to rest and become part of you. Mass, in the end, is just the name for being able to stop. And yet, if I had told a physicist in the 1950s that empty space was secretly full of a field that gives particles their mass, they would have looked at me as if I were describing magic. The idea sounds invented, almost mystical, a convenient story dreamed up to make the numbers work. So why do we believe it? Not because anyone wanted to. We believe it because in the early 1960s, the equations describing the forces of nature walked straight into a catastrophe, a contradiction so sharp that the entire structure of particle physics was on the verge of collapse. And the only way anyone could find to save it was to propose, against all intuition, exactly this: a field hiding in the vacuum. To see why such a wild idea became unavoidable, we have to go back to that crisis and meet the handful of physicists who, almost against their will, wrote the field into existence. So let us travel back to 1964. Part 6. The fix nobody asked for. To understand the crisis, you have to understand what physicists were trying to do in the early 1960s, and how beautifully and frustratingly it was failing. They were trying to describe the forces of nature using a particular kind of theory, a kind that had already triumphed spectacularly for one force and seemed like it should work for the others. The triumph was the theory of electromagnetism, the force behind electricity, light, and magnetism. It had been folded into the quantum world into a theory of staggering accuracy, one that could predict certain measurements to more than 10 decimal places, the most precisely confirmed theory in the history of science. And the secret to its beauty was something called symmetry. Symmetry, in physics, means that you can change something about your description of the world, and the physics stays exactly the same. It is a statement that nature does not care about certain choices. And it turns out that when you build a force out of a particular deep symmetry, the mathematics is extraordinarily elegant and well-behaved, and it makes sense at every scale, never breaking down into nonsense. The electromagnetic force came from exactly such a symmetry, and that symmetry was the reason the theory worked so flawlessly. So when physicists turned to the other forces, especially the weak nuclear force, the force responsible for certain kinds of radioactivity, they naturally tried to build it from the same kind of symmetry. They wanted that same elegance, that same good behavior. And here was the catastrophe. The symmetry that made the mathematics work had a brutal, non-negotiable side effect. It demanded that the particles carrying the force be completely massless. Massless, like the photon, the particle of light. The symmetry simply would not permit the force-carrying particles to have any mass at all. If you tried to write a mass for them into the equations by hand, the symmetry shattered, and the moment it shattered, the theory fell apart, spitting out infinities and nonsense, becoming as useless as the failed self-energy theory of the electron. The symmetry was all or nothing. Keep it, and your force carriers must be massless. Break it, and your theory dies. But the weak forces carriers are not massless, not even close. We can measure them, and they are heavy, among the heaviest particles known, each one weighing nearly 100 times more than a proton. So physics was trapped between two walls. The symmetry was necessary to make the theory sane, but the symmetry forbade mass, and the particles plainly had enormous mass. You could have a beautiful theory of massless particles that did not match reality, or an ugly broken theory of massive particles that collapsed into infinities. Neither was acceptable. For years, this was a genuine impasse, a place where the most powerful method in physics simply could not be applied to one of the fundamental forces, and nobody could see a way through. The way through, when it came, was almost sneaky in its cleverness. What if, some physicists wondered, the symmetry was still there in the underlying laws, perfect and unbroken, keeping the mathematics sane, but the world we actually live in was hiding it? What if the equations had the full symmetry, but the particular state of our universe, the vacuum we happen to sit in, did not display it? There is a difference, it turns out, between a law being symmetric and a situation being symmetric. You can have perfectly symmetric laws that nonetheless play out in a lopsided, asymmetric way if the world settles into a particular state that picks a direction the laws themselves did not prefer. There is a simple image for this, and it helps. Imagine a pencil balanced perfectly on its point. The situation is completely symmetric. The pencil has no preferred direction to fall. Every direction around it is equally likely. The laws holding it up do not favour north over east over south. But the pencil cannot stay balanced. It must fall, and when it falls, It falls one particular way, and the instant it lands, the symmetry is gone. Now there is a special direction, the direction it happened to fall, even though nothing in the laws chose it. The symmetry of the laws is still perfectly intact. It is the situation, the resting state, that broke it. Physicists call this spontaneous symmetry breaking, and it was the key that unlocked everything. The idea was this. Suppose space is filled with a new field, and suppose that field, like our balanced pencil, cannot rest at the symmetric value of 0. Suppose its most comfortable resting state is at some non-zero value instead, a value it must fall into the way the pencil must topple. Then the underlying laws keep their full, beautiful symmetry, which keeps the mathematics sane. But the vacuum, the actual resting state of the world, sits at that non-zero value, and that broken symmetry vacuum is what hands out mass. The force-carrying particles, interacting with the fallen field that fills all space, gain mass from it, even though the laws that govern them never contained any mass at all. The symmetry is saved, and the masses are explained, both at once, by a field that fell over at the beginning of time and never got back up. That field is the Higgs field, and the falling over is why it holds that non-zero value of about 246 everywhere in the vacuum, the value we stood inside in the sealed chamber. In the year 1964, this idea was worked out in a rush, almost simultaneously, by several physicists working separately, who arrived at the same answer from slightly different directions. Two physicists in Belgium, Robert Brout and François Anglais, published it first, in August of that year. A month or two later, working alone in Edinburgh, a quiet British physicist named Peter Higgs published his own version. And shortly after that, a trio of physicists, Gerald Guralnick, Carl Hagen, and Tom Kibble, arrived at it as well. 6 people, 3 papers, 1 revolutionary idea, all in a single year. I want to slow down on Peter Higgs himself, on one specific moment, because it tells you something about how strange and lonely a great idea can be when it is born. When Higgs wrote his paper and sent it off, he had added something the others had not emphasized. He pointed out that if this field really filled space, then poking the field, exciting it, should produce a new particle, a ripple in the field itself, a particle nobody had ever seen. His paper, with this prediction in it, was initially rejected by the journal he sent it to. They did not see why it mattered. So he revised it, sharpened the point about the new particle, and sent it elsewhere, and it was published. That predicted ripple, that brand new particle almost no one was asking for, would come to be called the Higgs boson, and finding it, proving that the field was truly there, would take the rest of the world 48 years. There is a beautiful subtlety in how the symmetry breaking actually works, and it is worth telling because it shows how careful the rescue had to be. When a symmetry breaks spontaneously, like the toppling pencil, the mathematics usually produces leftover massless ripples, unwanted particles that should appear and that nobody ever sees. For a while, this looked like it might sink the whole idea, trading one problem for another. But in the case of the Higgs field coupled to a force, something elegant happens instead. Those would-be leftover ripples do not become stray particles. They are absorbed into the force-carrying particles themselves, and the act of absorbing them is exactly what gives those carriers their mass. In the vivid phrase physicists use, the force carriers eat the leftover ripples and grow heavy. The unwanted massless particles and the missing masses solve each other. Nothing is left over, nothing is unexplained, and the once massless carriers of the weak force end up weighing almost 100 times more than a proton, precisely as observed. And notice which particle did not eat anything, because it matters to your everyday life. The carrier of the electromagnetic force, the photon, the particle of light, sits this whole process out. It does not interact with the fallen field in the way the weak carriers do. It absorbs no leftover ripple, and so it stays exactly massless, free to fly forever at the speed of light. That is why light is light. The same mechanism that made the weak forces carriers heavy left the photon weightless, and that single difference shapes the world you live in, separating the short-range force hidden inside atomic nuclei from the long-range force that brings you sunlight and lets you see across a room. One field, falling once at the beginning of time, sorted the forces of nature into the heavy and the weightless. Think about what that means as a human fact. A man sits in an office in 1964 and works out, on paper, that all of space must be filled with an invisible field, and that the field implies a particle nobody has ever detected. He can offer no direct evidence. He cannot point to it in any experiment. He simply follows the mathematics to a conclusion that sounds insane, that empty space is full, that mass is a wage paid by a fallen field, that a new particle must exist to prove it. And then he publishes it and waits. He was 35 years old. He would be 83 before the universe finally answered him. To understand how that answer came, and what it felt like in the room when it did, we have to leave the quiet offices of the 1960s and travel forward almost half a century to a machine 17 miles around, buried beneath the border of two countries, on a summer morning that a generation of physicists had been waiting their entire lives to see. Part 7. The 4th of July. To prove that the Higgs field was real, you could not simply look at empty space and see it, because the field gives no light and makes no sound. The only way to prove it existed was to find its ripple, the particle Peter Higgs had predicted, the Higgs boson. And to make that particle, you had to disturb the field hard enough to set it ringing, which meant concentrating an almost unthinkable amount of energy into a single tiny point of space, again and again, millions of times a second, and watching for the brief, faint signature of the field twitching in response. Building a machine that could do that took decades and the cooperation of thousands of people from dozens of countries. The machine they built is called the Large Hadron Collider, and it sits in a circular tunnel about 17 miles around, buried roughly 100 meters underground beneath the border of Switzerland and France, outside the city of Geneva. Inside that ring, protons are accelerated until they are moving at very nearly the speed of light, so fast that they circle the entire 17-mile loop more than 11,000 times every second. Then two streams of them, running in opposite directions, are steered into each other so that the protons smash together head-on. In those collisions, for an unimaginably brief instant, the energy concentrated into that tiny space is enough to do what nothing on Earth had done before deliberately. It is enough to make the Higgs field ring. When the field rings, it produces a Higgs boson, but that boson does not last. It exists for a span of time so short it can barely be called a duration at all, and then it falls apart, decaying into other, more ordinary particles that fly outward into the enormous detectors surrounding the collision point. You never see the Higgs boson itself. You see its wreckage, the spray of particles it leaves behind, and from that wreckage, painstakingly, you reconstruct the fact that it was there. It is like proving a raindrop fell into a pond, not by seeing the drop, but by measuring the ripples it left on the surface. And the trouble is that countless other processes throw off similar wreckage all the time. So the signal of a real Higgs is buried in a roar of lookalikes, and only by collecting and sifting an astronomical number of collisions can the true signal slowly rise above the noise. Two separate teams, each with thousands of physicists, built two separate detectors and hunted independently, on purpose, so that neither could fool itself. One was called Atlas, the other CMS. They did not share their results as they worked, precisely so that if both arrived at the same answer, no one could say they had simply talked themselves into agreement. Through the early part of the year 2012, both teams watched a small bump begin to grow in their data, a slight excess of collisions producing a particle of a particular weight a weight near 125 times that of a proton. Month by month, as more collisions piled up, the bump refused to fade. It sharpened, it grew more certain, and by the end of June, both teams knew, separately, that they had something real. On the morning of the 4th of July, 2012, the world's physicists gathered in an auditorium at the laboratory near Geneva, and many thousands more watched the broadcast from around the planet, some camping out overnight to get a seat. Among the people in that room was Peter Higgs himself, now 83 years old, who had flown in for the occasion. Nearly half a century earlier, he had sat alone and written down that this particle must exist, and now he had come to hear whether the universe agreed. The two teams presented their results one after the other, slide by careful slide, building toward the number everyone was waiting for, the measure of how certain the signal was. When the result came, it crossed the threshold that particle physicists treat as the line between a hint and a discovery. The signal had reached what they call 5 sigma, a level of statistical certainty meaning the odds of the bump being a random fluke were less than 1 in 3 million. Both teams had it. Both teams agreed, independently, on a new particle weighing about 125 times the mass of a proton. The Higgs boson, predicted on paper in 1964, defended through 48 years of doubt, had finally been seen. The field hiding in empty space was real. The room broke into applause, and the cameras turned to Peter Higgs, and the old man took off his glasses and wiped his eyes. He had spent most of his adult life as the namesake of a particle that might never be found, carrying the quiet possibility that he had been wrong all along, that the field was a mathematical fantasy and the vacuum was empty after all. And here, in a single morning, a generation of physicists who were not even born when he made his prediction handed him the answer. It was real. He had been right. Later, he would say that he never expected it to happen in his lifetime, and that he had simply not imagined the day would come. There is a sad shadow across that bright morning, and it should be told, because it is part of the human weight of the discovery. Robert Brout, who with François Englert had published the idea first, a month before Higgs, had died the previous year, in 2011. He missed the confirmation by less than 12 months. When the Nobel Prize for the discovery was finally awarded, in 2013, it went to Peter Higgs and François Englert, the two surviving originators most associated with the idea. Brout could not receive it because the prize is not given after death, and so a man who had helped solve one of the most profound puzzles in physics did not live to see his answer confirmed or his name honored. The universe took its time answering, and it does not wait for anyone. So now we have it, the full machinery laid out. The electron has no size and no place to keep material. Mass is not material anyway. It is bound energy. The vacuum is not empty. It is filled with the Higgs field, switched on everywhere at a non-zero value because it fell from symmetry at the birth of the universe. The electron interacts with that field, and the interaction gives it inertia, weight, mass. And the proof is a particle, the Higgs boson, predicted in 1964 and found in 2012, ringing in a machine 17 miles around. The question we started with, where does an electron get its mass, has an answer, confirmed to 5 sigma, honoured with a Nobel Prize. We could stop here, satisfied. But if we stopped here, we would be leaving out the strangest part of the whole story, and it is a part that turns the satisfying answer almost upside down. Because everything I just told you about the electron is true, and the electron does get all of its mass from the Higgs field, and yet the electron is almost weightless, and you are not made of electrons in any way that matters to the scale. When you step on that scale tomorrow morning, the number it shows you is almost entirely not the Higgs field's doing. The mechanism we worked so hard to understand, the field, the boson, the 48 years of waiting, accounts for only a tiny sliver of your actual weight. The rest comes from somewhere else entirely, somewhere we already brushed against and walked quickly past. It is time to go back and face it, because it is the most surprising thing about your own body that physics has ever discovered. Part 8. The twist that undoes the answer. Let me bring back a fact I asked you to put in your pocket several chapters ago, because the moment to spend it has arrived. The electrons in your body, the ones that do all the chemistry and form all the bonds, make up only about 3 or 0.04% of your total weight. Almost all of your mass is in the nuclei of your atoms, in the protons and neutrons packed at their centers. So when we triumphantly explain that the electron gets its mass from the Higgs field, we have explained the origin of a tiny fraction of 1% of you. The Higgs field, for all its grandeur, is responsible for the weight of the lightest, most negligible part of your body. The real bulk of you, the heavy core, has barely entered the story yet. So let us ask the harder question. Where do the protons and neutrons get their mass? They are the things that actually weigh you. And we already saw the first half of the answer, back when the easy picture of mass collapsed. A proton is made of 3 quarks, and those 3 quarks, added up, account for only about 1% of the proton's weight. The quarks do get their small masses from the Higgs field, just like the electron does. But their masses are tiny, and together they make up only 1/100th of the proton. So even inside the proton, the Higgs field explains only about 1% of the weight. The other 99% has to come from something else. And that something else is the answer that should genuinely change how you feel about your own body. The other 99% of the proton's mass is energy, pure energy, bound up inside the proton, weighing exactly as much as the equation says energy must weigh. Inside every proton, the 3 quarks are not sitting still. They are moving at tremendous speeds, near the speed of light, trapped inside an unimaginably powerful force that will not let them escape. That force, the strong nuclear force, the strongest force in all of nature, fills the inside of the proton with an intense field, and that field carries enormous energy, and the quarks racing around within it carry enormous energy of motion. And all of that energy, by Einstein's equation, is mass. The proton is heavy not because it is full of heavy material. It is heavy because it is a tiny container packed with violent trapped energy, and energy weighs. I want you to really feel the size of this, because the numbers are almost comic. The actual material inside a proton, the rest mass of its quarks, the closest thing to genuine stuff it contains, is about 1% of its weight. The other 99% is the energy of confinement, the energy of the strong force holding those quarks in their tiny prison, and the energy of their frantic motion within it. If you could somehow remove that binding energy, the proton would lose 99% of its mass. The thing that weighs you, almost all of it, is not substance at all. It is force and motion, locked into a space so small you cannot picture it, masquerading as solid weight. So here is the reframed truth about your body, and it is one of the most remarkable facts in all of science. You are not, in any meaningful sense, made of stuff. You are made of energy that behaves as if it were stuff. If you took all the actual material in your body, the genuine rest mass of all your quarks and all your electrons, the irreducible substance, and put it on one side of a scale, it would come to roughly 1% of your weight. The other 99% of you is bound energy, the trapped fury of the strong force inside your protons and neutrons, converted into mass by the most famous equation in physics. When you place your hand on a table and feel its solid weight, you are feeling, almost entirely, the weight of energy in confinement. And this is where the 2 great revelations of tonight finally stand side by side, and you can see how strange the simple word mass really was all along. The electron, the light part of you, gets its mass from an invisible field filling empty space. The proton and neutron, the heavy part of you, the part that is actually most of your weight, get their mass from energy trapped by a force? Neither answer is the schoolyard idea of mass as the amount of material. One is a field in the vacuum, the other is bound energy. The solid, simple weight you carry is built from two of the least solid things imaginable, a field you cannot see and a fury you cannot picture, and there is almost no actual substance in it at all. This also resolves something that might have been nagging at you. I told you the electron gets all of its mass from the Higgs field, and that is true. But I also told you the Higgs field accounts for only about 1% of ordinary matter's weight. Both are true at once, and now you can see why. The electron's mass is 100% Higgs, but the electron's mass is a vanishingly small part of an atom. The proton's mass is 99% binding energy, and the proton is almost all of the atom. So when you average over a whole body, the Higgs field's contribution shrinks to about 1%, not because it fails to give the electron its mass, but because the electron was always the featherweight in the room. The Higgs is the entire story for the light things, and a footnote for the heavy things, and you are mostly heavy things. Now, I have to add an important caution here, because it would be easy to walk away thinking the Higgs field barely matters, and that is not true at all. The Higgs field accounts for only about 1% of your weight, yes, but without it, you would not exist to be weighed. Here is why. If the Higgs field switched off, the electron would lose its mass and instantly fly off at the speed of light, because a massless particle cannot do anything else. And an electron moving at the speed of light cannot be captured into orbit around a nucleus. There would be no atoms. No atoms means no molecules, no chemistry, no stars that burn in a stable way, no planets, no biology, no you. So the Higgs field is responsible for only a sliver of your mass, and yet is utterly essential to your existence. It is small in the accounting and infinite in the consequence, the difference between a universe of atoms and a universe of nothing but light streaking through the void. There is a way to keep score on all of this that makes the strangeness impossible to dismiss. Suppose you went through your entire body and sorted every scrap of its weight into two buckets, one labelled the Higgs field and one labelled bound energy. Into the Higgs bucket would go the mass of all your electrons and the tiny bare masses of all your quarks. Into the energy bucket would go the binding energy of the strong force inside every proton and neutron. When you finished, the Higgs bucket would hold roughly 1% of your weight, and the energy bucket would hold the other 99%. The thing we spent half the night, and a Nobel Prize explaining, accounts for the smaller bucket. The thing we almost walked past, the bound energy, is nearly all of you. And the imbalance is not a quirk of human bodies. It is true of essentially all the ordinary matter in the universe. Every star, every planet, every cloud of gas, every rock and ocean and living thing is made overwhelmingly of protons and neutrons are made overwhelmingly of binding energy. So when you look up at a galaxy of hundreds of billions of stars and think of all that mass, you are looking almost entirely at trapped energy of the strong force, wearing the appearance of solid worlds. The Higgs field, magnificent as it is, supplies only the thin 1% rim around that enormous total, plus the indispensable little gift that lets electrons sit still so atoms can exist at all. The visible universe is, by weight, a structure built almost entirely out of confined energy, and we are a small example of the same construction. So we have followed the question to a place far stranger than where we started. We wanted to know where the electron gets its weight, and we found a field hiding in empty space. We wanted to know where our own weight comes from, and we found that it is almost entirely trapped energy wearing the disguise of solid matter. The everyday idea of mass, the amount of stuff, has not survived a single step of this journey. But I have been describing the trapped energy of the proton from the outside as a fact about numbers. To really understand what it means that you are mostly bound energy, I want to take you inside the proton And then I want to do something almost cruel. I want to reach for the dial that controls the Higgs field and turn it to 0 and show you what survives. Because what survives will tell you, better than any number could, what your weight has been made of all along. Part 9. You are mostly trapped energy. Come inside a single proton with me, one of the countless protons in the nucleus of a single atom in the tip of your finger. From the outside, the proton looks like a simple particle, a tiny positive speck. From the inside, it is anything but simple. It is a furious, churning place. 3 quarks are here, the closest things to solid pieces the proton contains, but they are not sitting quietly. They are racing around at speeds near the speed of light, and they are bound by the strong force, which behaves unlike any force you have ever felt. Around and between the quarks, the strong force fills the proton with a seething field, carried by particles called gluons, that flicker in and out by the countless billions, binding everything together with a grip nothing can break. Watch the quarks try to move apart, and you will see the strangest feature of this force. Most forces weaken with distance. Pull 2 magnets apart, and the pull fades. Move away from the Earth, and gravity loosens. The strong force does the opposite. The farther apart you try to pull 2 quarks, the harder it pulls them back, like a rubber band that grows tighter the more you stretch it. You can never pull a quark out of a proton, because the energy you pour into stretching the bond just keeps building, growing without limit, until it becomes so great that it spawns brand new quarks rather than letting the old one go free. The quarks are imprisoned, not by walls, but by a force that simply will not loosen its grip, and the energy of that endless straining grip is enormous. That energy is what you weigh. Sit with that. The frantic motion of the trapped quarks, racing near light speed, and the colossal energy of the strong force field holding them in their cell, together make up about 99% of the proton's mass. There is barely any material here. There is a tiny amount of genuine quark substance, the part the Higgs field is responsible for, and then there is this roaring ocean of bound energy, and it is the ocean that tips the scale. When you feel the weight of your own arm, you are feeling almost entirely the weight of this fury, repeated inside every one of the countless protons and neutrons that make you. Now let me do the cruel and clarifying thing. Imagine there is a dial in front of us that controls the Higgs field, and imagine we slowly turn it down towards 0, switching off the field that fills the vacuum. Watch what happens, piece by piece. First, the electrons. As the field fades, they lose their mass, and the instant they become massless, they tear away at the speed of light and are gone, and every atom in your body unravels in less than the blink of an eye, because there is nothing left to hold the electrons in orbit. The structure of all matter dissolves into streaking, weightless particles. That alone is the end of you, the end of atoms, the end of chemistry. The Higgs field's small contribution to your mass turns out to be the thread holding the whole tapestry together. But keep watching the proton itself, because here is the revelation. As the Higgs field drops to 0, the 3 quarks inside the proton lose their small rest masses too. And the proton barely changes weight. It loses that 1%, the sliver that was genuine quark substance, and then it sits there, still holding 99% of its original mass, because that 99% never came from the Higgs field in the first place. It came from the strong force, from the binding energy and the trapped motion, and the strong force does not care whether the Higgs field is on or off. The proton's weight was almost entirely its own internal energy all along. Switch off the field that gives mass to the fundamental particles, and the heavy core of matter shrugs and keeps almost all its weight. There is something almost vertiginous in that image, and I want you to stay in it for a moment rather than rushing past. We spent this whole journey learning that the electron gets its mass from the Higgs field, that this was the great answer, confirmed in a machine 17 miles around, honored with a Nobel Prize. And it is the answer for the electron. But your weight, the number on your scale, the heaviness of your own body in your own hands, would survive almost untouched if that entire mechanism vanished, because your weight was never mostly about the Higgs field. Your weight is the strong force, screaming inside your protons, frozen into mass. You are not a solid object that happens to contain some energy. You are bound energy that happens to behave at your scale like a solid object. Think about what this does to the ordinary experience of touching something heavy. You lift a stone and feel its mass resist you. That resistance, that heaviness, is the summed weight of trillions upon trillions of protons and neutrons, and inside each one, almost all of that weight is the trapped energy of a force, locked into a space a quadrillionth of a meter across. The stone feels solid and substantial and full. It is, in truth, mostly empty space, and the little that is not empty space is mostly not material but bound energy, the strong force held in confinement, wearing the mask of weight. The solidity of the world is real in its effects and almost illusory in its substance. You can lean on it, build on it, be crushed by it, and it is made, at bottom, of fields and trapped motion and almost nothing you could rightly call stuff. So the honest, complete answer to where your mass comes from is now in front of us, and it has two parts that could hardly be more different. A small part of you, the electrons and the bare quark masses, gets its weight from an invisible field that fills the vacuum, the Higgs field, switched on everywhere since the dawn of time. The overwhelming bulk of you gets its weight from energy, the strong force bound inside your protons and neutrons, converted to mass by Einstein's equation. Neither part is the simple substance you were taught to imagine. The mass you have carried your whole life is a field you cannot see and a fury you cannot picture, and there is essentially no solid stuff in it at all. There is one more thread worth pulling here, because it ties your weight to gravity in a way that closes a quiet loop. When you stand on a scale, what the scale measures is gravity pulling on you, and gravity, it turns out, does not pull on substance, it pulls on energy. Anything that carries energy also carries weight and feels gravity, which is exactly why the bound energy inside your protons is not some bookkeeping abstraction, but real, heavy, gravitating mass. The trapped fury of the strong force bends space-time and presses on the scale just as surely as any lump of material would, because to gravity there is no difference. Energy is what gravity responds to, and your protons are full of energy, so your protons have weight. The scale cannot tell and does not care that almost nothing it is weighing is substance. This is also why one of the oldest and most precisely tested facts in physics holds true for you. The mass that makes you hard to push, your inertia, and the mass that gravity pulls on, your weight, are always exactly equal, tested to better than 1 part in 1,000 trillion. They are the same mass, the same bound energy, seen from two sides. The energy locked in your protons resists being shoved and is pulled by the Earth in precisely equal measure, whether that energy came from the Higgs field or from the strong force. So the strange composite thing you are made of, a sliver of field-given mass and an ocean of trapped energy, behaves to gravity and to motion alike, as one seamless weight. The universe does not keep separate ledgers for the two kinds of mass. On the scale, they are simply you. You might think that with both halves of the answer in hand, the mystery is finished, the question fully closed. The electron's mass comes from the Higgs field. The proton's mass comes from binding energy. Confirmed, measured, Nobel stamped. And in one sense, that is true. But hidden inside the confirmed answer is a question that nobody on Earth can answer, a hole at the very center of the thing we are most proud of understanding. We can tell you that the electron gets its mass from the Higgs field. We cannot tell you why its mass is the exact amount it is, rather than larger or smaller. And the more you look at that simple-seeming gap, the wider and stranger it becomes. So let us turn now to what the answer still cannot explain, and find the locked room sitting in the middle of our greatest success. Part 10. The number no one can explain. We have an answer, and it is a magnificent one. The electron gets its mass by interacting with the Higgs field. The strength of that interaction determines how much mass it gets. Talk to the field weakly, be light. Talk to it strongly, be heavy. The electron talks to it weakly, and so it is light. That is the mechanism, and it is correct. But now ask the next question, the obvious one, the one a curious child would ask without hesitation. Why does the electron talk to the field as weakly as it does, and not more and not less? Why is the strength of that interaction the particular value it is? And here, at the very center of our triumph, physics goes quiet, because nobody knows. The strength with which each particle interacts with the Higgs field is a number, and physicists call it that particle's coupling. The electron's coupling is very small, about 3 millionths in their units, which is why the electron is so light. The top quark, the heaviest known particle, has a coupling of about 1, which is why it weighs as much as an entire atom of gold, despite being a single fundamental particle. In between are all the other particles, each with its own coupling, each a different value. And here is the uncomfortable truth. Not one of those couplings can be calculated. Not one of them can be derived from any deeper principle. We measure them. We look at how much each particle weighs, we work backward to find its coupling, and we write the number down by hand. The theory does not predict the masses. We feed the masses in. Let me make sure that lands, because it is easy to underestimate how strange it is. The Higgs mechanism is often described as the thing that explains the masses of the particles, and in a sense it does. It explains the mechanism, the how. But it does not explain a single one of the actual values. If you imagine the equations of particle physics as a great machine, the masses are not things the machine produces. They are dials on the front of the machine that we have to set by hand, by going out and measuring the real world. There are about 20 such dials in the complete theory, and the masses of the fundamental particles account for most of them. We can predict almost everything else with breathtaking accuracy, and yet the masses themselves, the very thing we set out tonight to explain, sit there as raw inputs, unexplained, unpredicted, simply observed, and the values are bizarre. The couplings of the known particles span an enormous range, something like 12 factors of 10 from the lightest to the heaviest. That is the difference between the weight of a single hair and the weight of a large building, repeated as the gap between two fundamental particles that are otherwise members of the same family. The electron, the muon, and the tau are three particles identical in every way except mass. The muon is about 200 times heavier than the electron. The tau is about 3,500 times heavier. They are the same kind of thing, governed by the same laws, interacting with the same Higgs field, and yet their couplings differ by these wild amounts for no reason anyone can find. Physicists call this the flavor puzzle, and it has stood unsolved for half a century. Why these numbers? Why this pattern? Silence. There is a second, even deeper version of the mystery, and it concerns the Higgs particle itself. The Higgs boson weighs about 125 times as much as a proton. That sounds heavy, and on the scale of particles it is, but according to the mathematics, it should be vastly heavier. When physicists calculate how the Higgs particle's mass should be affected by the constant quantum churning of the vacuum, by all the fleeting particles flickering in and out of existence around it, the calculation tries to drag the Higgs mass up toward the highest energy scale in nature, a scale called the Planck scale, which is something like 1,000,000 billion times larger. Every quantum correction shoves the Higgs mass toward that titanic value, and yet it sits calmly at a tiny fraction of it. For that to happen, enormous contributions would have to cancel against each other with a precision so absurd, so finely balanced, that it looks less like physics and more like a conspiracy. This is called the hierarchy problem, and it is one of the most discussed puzzles in all of modern physics. The Higgs mass is unnaturally, almost impossibly light, given everything that should be making it heavy. Imagine balancing a pencil on its point and coming back 1,000 years later to find it still balanced, perfectly upright. You would not believe it was an accident. You would assume something was holding it there, some mechanism you could not see. Physicists feel the same way about the Higgs mass. It is balanced so improbably that it cries out for an explanation. Some hidden mechanism that protects it, some new physics not yet discovered. The trouble is that the leading candidate for that hidden mechanism has not shown up. For decades, the favoured answer to the hierarchy problem was a beautiful idea called supersymmetry, which proposed that every known particle has a heavier partner particle, as yet unseen, and that these partners would naturally cancel out the corrections trying to inflate the Higgs mass, holding it gently at its small value. It was elegant. It solved several problems at once, and many physicists were confident the Large Hadron Collider would find these partner particles soon after it found the Higgs. But it did not. The collider has run for years, at higher and higher energies, and the partner particles have not appeared. Supersymmetry is not dead, but the simplest and most hopeful versions of it have been ruled out, and the hierarchy problem remains as sharp as ever, its elegant solution conspicuously absent. So the situation is this. We have explained how the electron gets its mass, and the explanation is real and confirmed. But wrapped inside that explanation are two great holes. We cannot explain why the electron's mass is the value it is, because the coupling that sets it is a number we measure and cannot derive. And we cannot explain why the Higgs particle, and therefore the whole scale of mass, is as light as it is, because every calculation says it should be enormously heavier. The answer we are proudest of has, at its centre, a locked room we cannot open, and the harder we look at the simple question of why anything weighs exactly what it weighs, the more clearly we see that our deepest theory describes the mechanism of mass perfectly while leaving its actual values a complete mystery. There is a tempting escape from this discomfort, and it is worth examining honestly, because many thoughtful people reach for it. Perhaps, the thought goes, the masses are what they are, because if they were different, we would not be here to measure them. Make the electron a little heavier, or the quark masses a little different, and atoms might not form, stars might not burn long enough for life, chemistry might never get going. So perhaps the values are not explained by a deeper law at all, but simply selected by the fact that only certain values permit observers to exist and ask the question. It is a real idea, taken seriously by serious physicists, and there is something to it. The masses we measure do sit in a remarkably narrow band that allows complexity to exist. Nudge several of them, and the universe becomes lifeless. But notice that this is not really an answer to why. It is more a statement about which questions can be asked and by whom. It tells you that observers will always find themselves in a universe compatible with observers, which is true but close to circular. It does not tell you what sets the numbers, only that we should not be surprised to find them life-friendly, since unfriendly values would have no one to be surprised. Most physicists treat this as a last resort, rather than a satisfying resolution, a thing you say when you have given up on finding a deeper rule. And the honest state of the field is that we have not given up. The search for a reason behind the masses, some hidden pattern in that wild span of values, is one of the great open quests of physics, and so far, the pattern, if there is one, has not shown itself. There is something almost humbling in that, and it is worth naming plainly, without fear. We built a machine 17 miles around. We confirmed an invisible field filling all of space. We traced your weight to a trapped force and a fallen symmetry, and at the end of all of it, if a child asks why the electron weighs exactly what it does and not a little more or less, the honest answer from the finest physics on Earth is that we do not know. The mechanism is understood. The number is a mystery. And that gap is not a sign of failure, but a marker of the frontier, the place where the known ends and the unknown begins. Beyond that frontier lie the ideas physicists are chasing now. Some of them serious and promising, some of them strange, and around them, as always around anything this profound, a fog of myth and misunderstanding that is worth clearing away. So let us step out to that frontier and to the ghosts that haunt it. Part 11. The Frontier and the Ghosts. Out at the edge of what we know, physicists are trying to find what lies underneath the Higgs field. And there are a few serious ideas worth telling honestly, each labelled clearly for what it is, an educated guess, and not yet a confirmed truth. The first is that the Higgs particle might not be fundamental at all. Remember that the proton once looked like a simple, basic particle, until we found it was made of quarks. Some physicists suspect the Higgs may be the same kind of illusion, not a true elementary object, but a bound state of deeper, smaller constituents, held together by a new force we have not yet identified. If that were true, the entire mass-giving mechanism would rest on a layer below the one we have found, and the hierarchy problem might dissolve because a composite Higgs would be protected from those runaway quantum corrections in a natural way. There is no evidence for this yet. It is a serious possibility, nothing more. A second idea is that there is more than one Higgs field or more than one Higgs particle. The version of the theory we have confirmed uses a single Higgs field, the simplest possibility, but many extensions of physics predict a whole family of related Higgs particles, several cousins where we have so far found only one. If those cousins exist, future and more powerful colliders might produce them, and finding even one additional Higgs particle would reshape our understanding of how mass is distributed among the particles. There are already proposals for the machines that could hunt for them, enormous colliders dwarfing even the current one, which may or may not ever be built given their staggering cost. For now, we have found one Higgs, and whether it is alone remains an open question. The third frontier is the most uncertain of all, and it concerns one particle we have mostly left out tonight, the neutrino. Neutrinos are fundamental particles, like electrons, but for a long time they were thought to be perfectly massless, sailing through the universe at the speed of light, passing through entire planets without touching anything. Then, around the turn of the century, experiments proved that neutrinos do have mass, a tiny one, almost vanishingly small, but real. And here is the puzzle. The Higgs mechanism can give neutrinos mass, in principle, the same way it gives the electron mass. But to do so, their coupling to the field would have to be staggeringly, almost absurdly small, far smaller than the electron's already tiny coupling, and nobody understands why it would be that small. Some physicists suspect the neutrino gets its mass a completely different way, through a second mechanism involving undiscovered, extremely heavy particles, a mechanism that could even explain why the neutrino masses are so small while it does so. If they are right, then there is a second story of mass, entirely separate from the Higgs, still waiting to be confirmed. So that is the honest frontier, 3 serious unknowns. Maybe the Higgs is composite. Maybe there are several Higgs particles. Maybe the neutrino's mass comes from somewhere else entirely. None of these is established. All of them are being actively chased. And every one of them, notice, is another way of admitting that the confirmed answer we are so proud of is not the bottom of the story, only the deepest layer we have so far reached. The question of where mass comes from is answered and unanswered at the same time, settled at one level and wide open at the level beneath. Now, Let me clear away the ghosts, the myths that have grown up around all of this, because they are everywhere, and they get in the way of the genuine strangeness, which is far more interesting than the inventions. The most famous ghost is the nickname you have surely heard, the one that calls the Higgs boson the God particle. People hear that name and assume the Higgs has something to do with the divine, with creation, with the meaning of the universe. It does not. The name has an almost embarrassing origin. A physicist writing a popular book in the early 1990s wanted to call the Higgs the goddamn particle out of frustration at how hard it was to find, and his publisher refused and shortened it to the God particle for the title. That is the whole story. Most physicists dislike the name precisely because it suggests a grandeur and a mysticism the particle does not possess. The Higgs gives mass to fundamental particles. It does not create the universe, answer questions of meaning, or have anything to do with any God. The second ghost is the idea that the Higgs field, because it fills all of space and connects to everything, is some kind of universal consciousness, a cosmic mind, a field that links all things in a spiritual sense. It is easy to see why the image is tempting. An invisible presence filling the vacuum, touching every particle, switched on everywhere, sounds like the sort of thing mystics have described for centuries. But the Higgs field is not that. It interacts only with certain particles, in certain specific ways, through precise mathematical rules, and it carries no information, no awareness, no intention. It does not connect your thoughts to the stars. It gives mass to electrons. The profundity is real, but it is the profundity of physics, not of mysticism, and dressing it up as cosmic consciousness only hides how genuinely astonishing the real thing is. The third ghost is the fear that the machine used to find the Higgs, the great collider near Geneva, is dangerous, that smashing particles at such energies could tear open a hole in reality or destroy the world. This fear surfaced loudly when the collider first switched on, and it returns periodically online. It is unfounded. The collisions inside that machine, as energetic as they are by human standards, are far gentler than collisions that happen naturally and constantly in the upper atmosphere, where particles from space strike the air with energies far beyond anything the collider can reach, and have done so for billions of years with no holes torn in anything. The machine is one of the safest, profound things humans have ever built. No portals, no danger. Only the patient work of listening for a field to ring. And there is one last ghost that deserves a kinder word, because unlike the others, it was once real science and a beautiful attempt. Long before the Higgs, in the early years of the 20th century, serious physicists genuinely believed that an electron's entire mass might be the energy of its own electric field. That mass was just a kind of stored electromagnetic effort. We met this idea earlier and watched it fail when the electron turned out to have no size and the math gave infinity. It was wrong. But it was wrong in a profound and prophetic way, because it was the first serious attempt to say that mass is not substance, but energy. The very idea that, in a completely different form, turned out to be true. The old electromagnetic mass theory was a ghost, but it was the ghost of a truth, and it deserves to be remembered as an honourable failure rather than a foolish one. Sometimes the wrong answer is pointing in exactly the right direction. With the frontier mapped and the ghost cleared, only one thing remains, and it is the thing we started with, all the way back at the beginning, the number on your scale, the weight you never question. We have taken it apart completely, followed it down past the easy answer, through the empty atom and the sizeless point, into the field hiding in the vacuum, and the fury locked inside the proton. It is time to put it back together, and to feel what it means to stand on a scale now, knowing what we know. So let us return, one last time, to your own weight, and see how different it looks from the inside. Part 12. The weight returned. Step back onto the scale, the same ordinary scale from the very beginning of the night, and look at the number. It is the same number it always was. Nothing about your body has changed. But everything about what that number means has changed, and you will never again be able to read it as the simple thing you once thought it was. Let us assemble, slowly, what that figure actually is, now that we have seen inside it. A tiny part of that number, a few hundredths of 1%, is the weight of your electrons, and every bit of that comes from the Higgs field, the invisible presence filling the vacuum, switched on everywhere since the universe was younger than a second. Those electrons are massless in their bare nature, born to fly at the speed of light, and it is only their endless interaction with that field that lets them sit still inside your atoms and have any weight at all. Without that field, they would scatter at light speed and you would never have existed. So a sliver of your weight is the wage paid by a field that fell from symmetry at the dawn of time, the same field whose ripple a man named Peter Higgs predicted on paper in 1964 and waited 48 years to see confirmed. And the rest of that number, almost all of it, 99% of the figure staring back at you, is energy. It is the strong force, locked inside the protons and neutrons at the centers of your atoms, the fury of quarks racing near light speed, and the colossal field that imprisons them, all of it converted into mass by the simplest and most famous equation ever written. When you feel your own weight pressing down, you are feeling, almost entirely, the weight of trapped energy. Force held in confinement, in spaces too small to imagine, repeated in every one of the uncountable particles that make you. You are not a solid object containing some energy. You are bound energy that has learned to behave like a solid object. So consider what has happened to the question we began with. We asked where the electron gets its mass, expecting, perhaps, a simple answer about what it is made of. And every layer of the simple answer fell away. The electron has no size, no inside, no material to be made of. Mass turned out not to be material at all, but bound energy. Empty space turned out not to be empty, but filled with a field that hands out inertia. And your own weight turned out to be almost entirely the trapped fury of a force, with the celebrated Higgs field responsible for only a fraction of 1% of it, essential to your existence and nearly absent from your weight at the same time. The weight you never questioned is the least solid thing about you. I want to return to the image of the field you are wading through, the one we corrected earlier, because it has changed meaning now in the way the best images do. At first it seemed the Higgs field was the thick medium giving you all your weight, the syrup you struggle through. Then we learned it is not syrup, it gives inertia, not drag. And now we know something further still, something almost tender. You barely touch that field at all. The part of you that interacts with it, your electrons and the bare cores of your quarks, is the faintest sliver of you. The ocean of the Higgs field laps against the lightest edges of your being and gives them their small weight, while the great bulk of you is held together by an entirely different power, a force screaming silently inside your every proton. You live inside an invisible field and are made almost entirely of something else. And the locked room is still there, at the center of it all, and I do not want to paper over it, because its presence is part of the truth. We can tell you the mechanism, we cannot tell you the number. Why the electron's coupling to the field is the precise tiny value it is. Why the masses of the particles span the wild range they do. Why the whole scale of mass sits as improbably light as it does. These remain unanswered by the finest physics on Earth. The point with no size that still weighs something has given up the secret of how it weighs, and kept the secret of why it weighs exactly that much. The deepest question about your own body, the simple why of your own weight, is still open, still waiting, somewhere out past the frontier. There is a kind of peace in that, if you let there be. We are so used to the idea that science has explained the ordinary world, that the everyday is settled and only the exotic remains mysterious. But here is the most ordinary fact imaginable: your own weight, the number you read without a thought, and it opens directly onto the unknown. You do not have to travel to a black hole or the edge of the universe to stand at the border of human understanding. You only have to stand on your bathroom scale and ask, with enough patience, where the number comes from. The mystery was never far away. It was holding you up the whole time. So the next time you feel your own weight, the heaviness of your body settling into a chair, the pull of the ground through the soles of your feet, let it mean what it actually means. You are feeling an invisible field that fills all of space, pressing its small gift of mass into the lightest parts of you. You are feeling the trapped fury of the strongest force in nature, locked inside particles smaller than thought, making up nearly all of what you weigh. You are feeling energy that has taken the shape of substance, fields that have taken the shape of solidity, a structure so empty and so strange that it is a wonder it holds together at all. And it does hold together every moment, well enough to carry you through a life, well enough to let you lie here now and consider the question. The weight you never question is a field you cannot see and a force you cannot picture, bound into the brief and beautiful arrangement that is your body by laws we have only begun to understand. You weigh what you weigh because the universe is far stranger than it lets on, because empty space is full, because energy is heavy, because a point with no size can still tip a scale. And somewhere in that answer, in the part we have solved and the part we have not, is the quiet reassurance that the world has not run out of wonders, that the most familiar facts still have flaws beneath their flaws, and that you, lying here, are made of the same deep mysteries as the stars. Rest now. The field will hold you, as it always has, whether or not you ever feel it there.